Therefore, my second step is to explain exactly the context and what are the assumptions we are going to take to develop ANOVA test. Assumptions obviously are already very important and they have to be checked because the calculations behind the technique are based on these assumptions. That's the reason why I'm going to list them here and on the next whiteboard. Therefore, we assume that we have xi1, xin. This is a sample of IID data. But for group I, for gasoline I, for fixed I, therefore for gasoline 1, we have one IID sample, for gasoline 2 the same, and for gasoline 3 the same as well. Therefore 3 in our example, 3 IID samples. For fixed I equals 1 up to M. We have M groups in our situation, 3 gasolines, 3 brands. Okay, that's for the sample we have. What we had in the table in the previous whiteboard was in fact the observation of these 3 samples for M equals 3, for the 3 gasolines. Next, we add some assumptions which are very useful. You know that in hypothesis testing theory, the normality, for example, the normality, each data xij, therefore each data in the table, is in fact the observation of a normally distributed random variable with mean mu I and with variance sigma square. Therefore you see mu I varies from I equals 1 to M. J here varies to j equals 1 to n. Obviously n data per sample for fixed I. What we observe is the normality. First, this is a strong assumption. Second, very strong assumption, what we name the homoscedasticity. Look at this here. You have sigma square which has no index I. If we look at mu has an index I, meaning that the mean is different according to the group. Sigma has no index I, that means sigma is the same for each group. That's a big assumption which is named usually homoscedasticity assumption. When we write that, we are going to try to check, to give the tools after to check these assumptions. But just before, let me write this assumption in another way that makes the interpretation of assumptions easier further. Xij is in fact mu I plus epsilon ij, where epsilon ij is in fact normally distributed with mean 0 and variance sigma square. Indeed, this is equivalent obviously. Xij, if we write xij equals mu I, that means its mean plus epsilon ij obviously as the distribution of xij minus mu I, and the distribution of xij minus mu I, this is obviously a normal distribution with mean 0 and with variance sigma square. We are going to use this kind of way to see the model. We will name that the model. This is the model we assume under the ANOVA with one factor. Let's see in another way, what does this assumption mean? This assumption means this graph. For this graph we could take, okay, this is here, for the x-axis you have the total millage. You have the millage for gas 1, millage for gas 2, millage for gas 3. No, sorry, this is the opposite. Millage for gas 1 with mean mu 1, millage for gas 2 with mean mu 2, and millage for gas 3 with mean mu 3. And we can see this assumption. We can see what does this assumption mean. What does this assumption mean? That means that the random variable in each group only differ by its mean. Each random variable in each group is normally distributed. We have exactly the same shape, the same bell-shaped for each of the distribution of the random variables in the group. They all have the same variance. That means the same dispersion here. The only way that the distribution differ is through the mean. mu1 is different from mu2 and is different from mu3. But that corresponds to a question we had on the first whiteboard. I said here the main objective is to see if the performances or the total mileages of my motors are the same according to the gasoline. This is a very fuzzy question in a way. This is a fuzzy question. Are the groups of 5 motors the same? That's the question. Therefore, when we add assumptions like this, we assume that in each group you have the same bell-shaped distribution. You have the same variance, the same dispersion. That means that the question to say if the question which is are the groups the same reduces to a very simpler question in this context, which is are the means of the group equal? Since the groups are already the same with their other characteristics. Normality is the same in each group, homoscedasticity is the same in each group. The groups can only differ by their mean. That means that the question, are the groups the same, reduces to the question, are the mean the same? That means that the test we will achieve will assume, under the null assumption, that all the means are equal. That's what we are going to see after. Now, just say to check these assumptions, that means normality and homoscedasticity, we have, as you already know, a lot of tools. First, for the normality in each group, that means that you construct a QQ plot. A QQ plot in each group. That means here we have 3 groups. You have to construct 3 QQ plots. For example, QQ plots or other tests. It's possible, but one possibility is to construct 3 QQ plots to check the normality in each group. To check the homoscedasticity, you also have tests explained in other videos. You have box plots, which is something which is very known by everybody, by basic courses of descriptive statistics. But you also have very simple ways to assess homoscedasticity at a first sight, let's say. Let's look at this. Let's look at this small graph. On the x-axis here, do you see that the x-axis here, you could put the group 1, group 2, group 3, and you could put on the y-axis the total millage. And here you put the dots. You put the dots corresponding to the millages of the different cars. And here, for example, you see that the dispersions in the 3 groups are more or less the same, I would say. But you could have different situations where you have a dispersion of the dots, for example, in group 2, which is very larger than the dispersion of the dots in the other groups. In this case, you would say we have a problem with homoscedasticity. Homoscedasticity is not necessarily checked. That's not a reason to reject immediately the application of the ANOVA test. But it's something that has to be said somewhere. That has to be said in order to say that maybe there is a problem in the results in the ANOVA. Obviously, when we look at these assumptions, most of the time, they are not completely checked. They are not completely true. In fact, in practice, in a way, they are always wrong. But usually in practice we say that it's not a too big problem, it's not too serious. Because in fact, an ANOVA test is a test. That means that the end of the test is only yes or no, reject or not reject the null hypothesis. That means that, okay, if you are not too far away from these assumptions, that won't change a yes to a no or a no to a yes. You know, at the end of a statistic test, you have a value. If this value is in the critical region, you reject. If the value is in the acceptance region, you don't reject. But anyway, if you are not too far away from the assumptions, the final statistics which is constructed, usually it doesn't vary too much, and therefore the value changes a bit. But that doesn't mean that the statistic is going to go from the critical region to the acceptance region, or from the acceptance region to the critical region. Usually the statistic stays in the region, in the right region, I would say. Next, another thing is that, yes, normality is, if you have very big data set, we can also say that normality is not necessarily useful, because the results of the ANOVA are correct asymptotically as well. Therefore, normality for small sample is very important, but for larger sample becomes less and less important. Therefore, there are two reasons to say, okay, the assumptions have to be checked, but if they are not completely satisfied, is this not too serious, I would say. It's not a too big problem, because if we are not too far away from these assumptions, the final result, yes or no, of the ANOVA test won't change. That will be the same binary result. That would be, it's very seldom that the result completely changes, only due to the fact that one assumption is not completely satisfied. But if we are too far away from these assumptions, obviously, that's a problem. Okay, that was for the first big assumption in ANOVA with one.